Hello and welcome back. So this video is for class 12 and today we will start with the new chapter, which is chapter number 10, wave optics. So previously we finished with the chapter of ray optics. So in ray optics what we imagined? We imagined rays of light, where we imagined that light is moving in a straight line, correct? And then we were able to see different phenomena like reflection, refraction, correct? We were able to have formulae for mirrors and lenses. So that part was called as the ray optics. Now we are not going to treat light as rays. We are actually going to treat it like a wave, and that is what we are going to see in this particular chapter. Okay, so before we begin, just a little background of why we are having two kind of treatments when we talk about light. Where in the first part we spoke about it like rays, and now all of a sudden we are seeing they are waves. So actually scientists, they have always tried to understand what is meant by light. So there were two theories given. One was Newton's corpuscular theory. Okay, now what is the corpuscular theory? The corpuscular theory will assume that light will exist in the form of particles. That is, if you are having any light source, let us say we are lighting a candle, correct? From that candle flame light is coming out. So Newton supposed that from that light actually particles of light are coming out, and that is called as the corpuscular theory. He said that there are small particles which are called as corpuscles, right? And these particles, when they come out, they enter the human eye, correct? And it is because of these particles that we are able to see a particular object. Newton also supposed that different colors will have different sizes of the particles, correct? But of course there were many shortcomings in this theory of the corpuscular theory. So to remove those shortcomings, another theory that was given by Christian Huygens, that theory is the wave theory. And of course in this chapter we are going to talk about this wave theory. Now don't worry about the corpuscular theory, correct? It has been disproved many times. Means we know very well that there are no corpuscles, there are no particles of light, correct? So now we believe in the wave theory. But of course after two chapters we are again going to go back, correct? And then we will talk about Albert Einstein, where we will again treat light as particles, but not as corpuscles, particles which are known as photons, correct? So of course now in your mind there is going to be a confusion that what do we say light is? Do we say light is a particle or do we say light is a wave? So actually light has this dual nature. Dual nature means it displays some properties like particles and some properties like waves, correct? That is called as the dual nature of light. It is a very interesting phenomena in our nature, correct? But again, for this chapter we will focus on the wave theory. So for this purpose, let us say that light is a wave, and then we are going to see different properties and we are going to explain the phenomena of light considering it is a wave. So let us start with understanding the Huygens principle. Now what is Huygens principle? So what Christian Huygens, he suggested there are no particles of light. Okay, Christian Huygens suggested that light is actually produced in the form of waves. So imagine there is one point source of light, right? For example, it could be anything. It can be a candle. You have lighted a candle. Now that is our point source. So Christian Huygens said that when you have a source of light, this source of light is going to create waves, right? So it is going to create a lot of waves in this manner. Now of course Christian Huygens thought that they are actually longitudinal waves, but now we know that they are actually transverse waves, right? But anyways, the principle will remain the same. So these are the waves that are created by our source of light. Now all these points, they are on the same phase, so we can call this as a wave front. Okay, what is a wave front? A wave front is locus of all the points on which all these light waves have the same phase. They are vibrating in the similar manner, correct? So this is a wave front. Now for the Huygens principle, Huygens says that a wave front acts in such a manner that every point on the wave front will now become a secondary source of light. Means our primary source, the original source of light, has created this one wave front, right? Now every point on this wave front will now become its own source of light, correct? It will now act as a secondary source. And now because it is acting like a secondary source, every point here will also create its own waves of light like this. Correct? So what we get, because of this one wavefront, we get another wavefront. Now this is called as a secondary wavefront. Okay, and once again what will happen? On this wavefront also, every point will act like a source of light. It will create its own wave, and then we keep on getting these wavelets in this manner. Getting the idea? That is the Huygens principle, and that is how Huygens says light is able to propagate. That means one point source of light will create one wavefront. That wavefront will give rise to other waves, and I hope you remember we spoke about this in electromagnetic waves as well. Electromagnetic waves, they have this self-sustaining property. They give rise to themselves, and basically that is why later on then when Maxwell's equation were given, we understood that this behavior can be explained by thinking that light is actually an electromagnetic wave. So anyway, so this is the Huygens principle, very easy to understand. Every point of the wavefront acts as a secondary wavefront, creating another wave of light, correct? And this is how light is getting propagated. Then of course, now since we are considering light as a wave, all the properties of waves we can give it. We can have a wavelength for it, we can have a frequency for it, correct? We can find its velocity, which will be given by frequency into wavelength, correct? So that is the Huygens principle. Now, one of the biggest problems in considering light as a wave is that any kind of wave will need a medium for traveling, correct? So that was the biggest opposition given to Christian Huygens theory, was that if you are saying light is a wave, then how is it moving? Because we see that light moves in a vacuum as well, right? Even when there is no medium present, light is traveling. So Christian Huygens said that there is a material which is called as ether, correct? He said this is a medium which is present everywhere, right? And he said it is because of this ether that light is traveling. So when we say waves of light, they are actually moving in the ether. Of course, now we know that ether is not present anywhere, correct? We have done extensive experiments to see, and we have not found the presence of ether. Then if there is no ether, then how does light move? Again, as we have seen, because light is an electromagnetic wave, correct? Because of its electromagnetic properties, even without any medium, light can actually move through a vacuum as well, correct? So now generally we accept the Huygens principle with minor changes, correct? We know there is no ether, but we know that this theory of light, this is very correct, and then we can study and we can analyze many phenomena considering the Huygens principle. Now let us talk about wave fronts. Okay, so if you are having a point source of light, a point source of light is going to create a spherical wavefront like this. It's a three-dimensional structure, and of course by Huygens principle, this spherical wavefront will give rise to another spherical wavefront, which will give rise to another spherical wavefront, right? So one spherical wavefront will keep on moving, it will keep on expanding by the Huygens principle. So that is a spherical wavefront. If we consider a small part of this spherical wavefront, correct, we can have the wavefront looking like this, correct? This is called as a plane wavefront. Okay, plane wavefront. So actually all the wavefronts are actually spherical in nature, but a small part of that, for example light coming from the sun, so actually sun is creating spherical wavefronts. But on the earth, if you create let us say you consider your window, okay, it is very small of that larger sphere, it's a very small part of that sphere, so you can actually consider that to be a plane wavefront. Okay, and again Huygens principle will come into the picture. Every point on this wavefront will act like a secondary source, it will create its own waves, and we will get another plane wavefront. So one plane wavefront will give rise to another plane wavefront, correct? So that is the idea behind wavefronts. And why we are talking about wavefronts is that when we do our derivations, we won't consider the spherical part, we will consider them as plane wavefronts, because as I said, we consider a small part of that spherical and a smaller part on that sphere, we can actually consider it as a plane wavefront. Now we will move to a very important question, that is we are going to explain reflection and refraction using Huygens principle, using the wave theory. Okay, now I try to keep the nomenclature same as that you are seeing in the textbook, so that when you see this diagram in the textbook, okay, it will look the exact same. So first we are going to find out, we are going to explain the laws of refraction using the wave theory. Okay, so this is our plane wavefront AB. Okay, this is the boundary of separating two medium. Here we are having medium 1 and here is medium 2. So initially let us imagine medium 1 is a rarer medium and medium 2 is a denser medium. Correct? For example, you can imagine medium 1 is air and medium 2 is glass. Right? And this is the boundary that is separating the two media. So this is our plane wavefront AB, which is moving towards the second medium. Right? Now what we want to do is we want to find out the refraction. We want to find out Snell's law if it is applicable using the Huygens principle. So what we will do, let us use the Huygens principle now. So this is our plane wavefront AB, right? At time t equal to 0, okay, this part A has reached the surface, but you can see part B is still farther away from the surface of the medium, right? So let us say after some time t, this wave, that is this ray, is going to reach the surface. Let us call this point as C. Okay, so the ray reached from B to the point C, and how it reached? Actually, what happened? Every point on this wavefront AB started acting like a wave. Okay, and then it created its own wavefronts. So the wavefront from B has reached the point C after some time t. Now let us say the velocity of light in the first medium is v1, velocity of light in second medium is v2. Then we can say that BC will be equal to v1 multiplied by t, right? And how can we say that? We know distance is equal to speed into time. So BC, this length BC will be equal to v1 multiplied by t. T is the time taken to reach from B to C. Let us call this our first equation. Now, when a wave is created from B, at the same time wave will be created from A as well by the Huygens principle. To find that wave, we'll have to create a sphere having a radius that is equal to after time t. So, this will be the wavefront that will be created from the point A. Now, when the wave is traveling through this medium, what will happen is the velocity is going to change. It is going to be v2, right? So, the wavefront that is going in this second medium, the radius of that wavefront will be equal to v2 multiplied by t. In that same time interval, another wavefront is created. Then, how do we find out the final wavefront in that second medium? That will be found by, let us see, this is the sphere that we created inside the second medium. We'll have to draw a tangent from point C to that sphere, and then we will see that tangent meets some point over here. Let us call that point as E. So AE will be the ray inside that. Okay, getting the idea? And how much is AE? AE will be equal to V2 multiplied by T. So let us write it, AE equal to V2 multiplied by T. Let us call it our second equation. And then this EC, this wavefront EC, this is actually our refracted wavefront. Okay, now just so that there is no confusion, here is what happened. AB was our incoming incident wavefront. A reached the surface, then B was still not reaching the surface. Then waveforms were created. From B, the waveform reached C. It took time t and the length covered was V1 into t. At the same time, from A wavefront was created, it reached the point E and the length was V2 into t in that same time interval. And both these points were in the same phase. Thereby we got the refracted wavefront EC. Correct? I hope till now everything is clear. So I hope this construction is understood. If you understand the construction, the remaining part is simple geometry. Okay. So this is the case that happened. AB incident wavefront, EC refracted wavefront. Now let us draw a normal at point A. Of course, angle between incident ray and the normal, this will be angle of incidence I. Again, angle between refracted ray and the normal, this will be angle of refraction R. Now because this angle is I, by geometry you can see that angle BAC will also be equal to I. And since this angle is R, the angle over here, so the angle ACE will also be equal to R. Okay, now of course if any confusion is there, just try to analyze it. Okay, very easy to understand. So we got now BAC equal to angle of incidence and ACE is angle of refraction. Fine. Now let us do the derivation part. So we know that sine of I will be equal to, this is I, sine of I will be opposite upon hypotenuse. So what is opposite to I? BC. So it will be BC upon hypotenuse is AC. Right. How much will be sine of R? Sine of R will be equal to, again, opposite upon hypotenuse. What is opposite? AE divided by hypotenuse is once again AC. So you can have sine of I upon sine of R. So if you find sine I by sine R, it will be equal to BC upon AC divided by AE upon AC. So you will see that AC gets cancelled. You get BC upon AE. Right. And already from equation 1 and 2, we have the values for BC and AE. So we can write. So from equation 1 and 2, we can write BC as V1t and AE as V2t. So this equation will become V1t divided by V2t. T gets cancelled, and so we are left with sine I by sine R is equal to V1 by V2. Okay, this was the equation we wanted. Let us call this equation number 3. This is equation 3 that we got, which is sine I by sine R is equal to V1 by V2. Now we know that if N1 is absolute refractive index of first medium, it will be equal to C upon V1, and if N2 is the absolute refractive index of second medium, N2 will be equal to C upon V2. Thereby you can say that N2 by N1 is equal to C by V2 divided by C by V1, which is nothing but equal to V1 by V2, which, comparing with equation 3, you can therefore write N2 by N1 is equal to sine of I upon sine of R. Or rearranging, you can write this as N2 sine R is equal to N1 sine I. And this is nothing but the Snell's law, which is the law of refraction. So using Huygens principle, we have derived the Snell's law, which proves that you can use wave theory to explain the phenomena of refraction. Okay, now I understand this would not have been so easy to grasp. Correct. We did a lot of manipulation, we did a lot of imagination here. So what my suggestion is, do this derivation, write it one more time, read from the textbook. If you are having doubts about this, let me know, because after this we are going to see more such derivations, right? We are going to prove reflection using the same principle. So before we do that, it is important that you understand this concept properly. So make sure you go through this, read the textbook, and if there are doubts, let me know.